this block 3 here. But DE builds, right? There's skills that we need, and they build and they build and they build and they build. Now, binary is sort of one of those skills, and it's sort of not. I mentioned yesterday that like 0 to 15, those are ones that they're going to want to be able to do, right? Be able to count from 0 to 15 in binary. Beyond that, like being able to convert 58 or 1022 to binary, it's not a skill that they're really going to need in the class. It's one of those skills, and I'll talk about this a lot, that I kind of put the line between, okay, do you need it for the course or do you need it for the end of course assessment, right? And so just for 2 seconds, I'm going to talk about that for those of you who are unfamiliar. At the end of this class with your students, not in the end of our training, but at the end of the class with your students, they'll be taking the end of course assessment. Okay. Now, in theory, you can do nothing with this, right? They can just take it and you can be like, all right, whatever. You don't have to do anything with the numbers. You don't have to use it as a grade. It doesn't affect them in many ways. But Project Lead, the way it uses that to sort of evaluate their curriculum. If a nation of 100,000 kids does really poorly on binary, they can be like, we need to up our game on our binary curriculum. But where it gets tricky is that some states put more weight on these tests, and some districts put more weight on these tests, and some colleges offer college credit if you do well enough on these tests. And so sort of along the way, there's been more meat put into this end of course assessment. So it's fine for me to be like, whatever. If they do well, they do well. They don't, they don't. It is what it is. But depending on your circumstances, it might matter more. Do I have any Florida teachers in here? Anybody Florida? Randall's a Florida teacher. Florida, like, you guys get money or something if kids do well on that test. I think there's like a little bonus or something, right? Does that sound right?
Yeah. The outgoing teacher said it's something like $25 per kid for passing.
Right. So like
some Florida 100 and something kids. So
right. So some Florida teachers, rightly so. Like that's nothing to ignore, right? If the kids do well enough on it, that's a decent chunk of change. So I often tell kids, Zach wants to know, Randall, is it to you or to your department? I think it's to the teacher, right? Yeah, it's to the teacher. That's fun money. Anyway, there are 4 universities that I know of that offer transcripted college credit. So for example, you pay X amount of dollars to Missouri S&T, and then you have electronics engineering from Missouri S&T on your transcript, and then you can transfer that wherever you want. And for some kids, that's pretty important, right? That's 3 credit hours they don't have to take at whatever university they end up at. So moral of the story is, depending on what you're going to do with it, this end of course assessment might be more or less important. So what I do in my class is I make a whole big speech about it in the beginning of the year. And I say, there's going to be times where I tell you things, and if you're planning on doing well on the end of course assessment, you're going to want to put a little more time in, right? That's really, for those of you who teach POE, I'm huge on that in POE, because there's so much in POE that like is basically academic, like stress strain calculations and thermodynamics and stuff like that like we don't do a bunch of labs with. It's just, it kind of is what it is. But I'm like, if you want to do well on the EOC, you need to knock out those equations. You need to be better at truss calculations. You need to, put in some extra oomph. Anyway, long story long, binary is one of those things. 0 to 15, yes, they should know it. Beyond that, it's not so critical. There is, if you look at the Windows calculator, let me share my screen real quick. Share. Hello. Oh, that's not what I meant to do. There we go. So here's a Windows calculator, right? There's one built into Windows. If you click these little 3 lines up here, people call that the hamburger. If you click those little 3 lines up there, you can actually choose programmer mode. And when you go to programmer mode, what you'll notice is like, if I want to, like the number 75, for example, it actually puts the little binary conversion right there. So I can see like, oh, 75 is 01001011, right? That's binary for 75, which is nice. Or if I want to know what 121 was, whoops, 121, that's 121 in binary. You can go the other way too, which is cool. You can click bin up here, and then you can put in a number. I like, this is just simple feature, but I want to high five the programmer who grayed out all the other numbers. So when I'm in binary, I can only hit ones and zeros. I like that. So you can put in whatever binary number you want, and it tells you what the decimal equivalent is. And hexadecimal and octal, by the way, while we're at it. So I show you this one so you guys can check your work and you write, tests or quizzes or whatever you want to do. So this thing is kind of neat. But also, again, it's not a thing that those conversions are crazy important, especially above 15. So, okay. All right. Okay. And the last thing I want to talk about yesterday was the breadboarding assignment. I just want to remind you that the breadboarding assignment you did yesterday is not something that kids do in class. Okay. That is specifically written just for this training. The kids in class will do 115C. So you remember in multisim, you put together some resistor circuit, and you measured it. They'll physically build that. But there was no way to get like the right resistors to you guys in this kit without it being a fortune. So that's why you only have, I think you have 4 or 8 of the same value resistor or something. That was the only way to make it work. We couldn't source the right resistors to get them to you. Now in your class kits, in your classroom, you'll have the resistors that are laid out in the activity. You can just do 115C, but we couldn't have you guys do that one. So that's why we wrote this separate activity just for you to do that breadboarding. Okay. So just a reminder, if you go in your classroom and you're like, where the heck is this thing? It's not there. It doesn't exist. Okay. So any other questions from yesterday on content, on pedagogy, on how I present things, on schedule, anything like that pops into your mind while I'm setting stuff up here? All right. So for Taylor said, what do I do for the measured value in 114? So in 114, there's a chart, 10 resistors, and in the real world, you would measure 10 different resistors. Well, you guys don't have 10 different resistors. So as you recall, a couple of options. You can, of the resistors that you have, you take your multimeter out and you measure your resistor. All your resistors are the same nominal value, but they should measure differently, give or take, because of tolerances. So that's what would go in that measured value. Or if you watch the video and it's your turn and use those values, some handsome gentleman was in there measuring, so you get the measured values in that video as well. So those are 2 different options for how to complete 114. Okay. Side note on that, for those of you who are walking into labs wherein the previous teacher was less than organized, a nice side benefit of this lab, of this activity 114, is you can just take that bowl of resistors and give them to your kids for this lab and be like, here, you figure it out. Grab 10 resistors from this random potluck, figure out what they are, and put them back in the right spot. Every year I end up with like kids left random crap out on the desks and I sweep it into a bowl or whatever. And then the next year I'm like, boop, here we go. And people are like, well, what if the kids are wrong? Like, it's still better. You put 1 or 2 in the wrong spot. It's still better than having a whole bowl full of random resistors. So that's a nice little teacher tip for you. Okay. So we're going to do 115A now. So this is going to be a long note-taking session. So if you want to get your pencil paper ready, however it is you want to take some notes, you can kind of follow along here how I'm doing these notes. If you do not know Ohm's law, series parallel, equivalency, all that kind of stuff, this is new content for you, which is great. If you are familiar with this, then pay special attention to how I'm teaching it, right? What words I use and how I lay them out, how I do my examples, all that kind of stuff, okay? That's the big takeaway on this. Share. iPad. Install. Don't be like that. Okay. So this is what we're doing here is called circuit analysis. Okay. This pen may not work for me. Yeah, I don't think that's going to do it. I don't think that's going to do it. All right. So circuit analysis, you can take classes, college classes in this. Like when I was in college, there was resistive circuits 1 and resistive circuits 2, and you're talking a year of what we're doing here. Physics teachers love to just heap these problems on kids because they're really easy problems to make, and they're kind of like almost like a logic puzzle. But it's a big part of analog electronics. So what we need to talk about first is what they call circuit configuration, or the idea that there's a difference between series circuits, okay, and parallel. I tell kids, they never understand as a teacher the fear when you're spelling something on the board. You're like, do I know how to spell this? Parallel. Okay, there. I think I got it. All right. So series and parallel. Okay. So a series circuit has one path. So for example, if I have like a little power supply here, I might have a bunch of resistors. There's only one path from the positive end of this power supply to the negative. There's no options. There's no branching. It goes all the way around. Only one path. Okay. Whereas parallel circuits have more than one path. Now, an important distinction for kids, these are not geometrically parallel, although oftentimes people draw them geometrically parallel just by like default. You'll see them in geometrically parallel. And I almost like to draw that distinction immediately. I'll draw my little power supply, and then I'll draw a resistor going that way and a resistor going this way. Just to be like, it is not a geometric parallel thing. Okay. What it means is both of their sides are kind of connected together, right? And that's my more than one path, because when the electrons get here or here, depending on your look at it, they branch, right? You have different branches for them to go on, different paths. Okay. And we can draw more If I want, I can put more resistors in parallel. See, they all come back to the same line. They're all connected to the same line up here. So they branch, 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 branch. Parallel circuits have more than one path. Okay, so first we need to look at a circuit and be able to say this is a series circuit or this is a parallel circuit. So that's the first big thing. Now, what circuit analysis is all about is solving for those three big things: current, voltage, and resistance. I'm out of room. Current, voltage, and resistance. Those three things, those three quantities, we're trying to solve for those in a circuit. So the understanding is we may not have all of that information, and we're trying to predict it. We're trying to solve for it, because if we're trying to build a circuit, we need to know how much voltage is here or there or here, how much total current there is, or whatever the case may be. We need to be able to predict what that is. Okay. Now, the first tool we're going to use, and a really, really, really important one, is called Ohm's law. Okay. Now, Ohm's law works for both series and parallel circuits. All right. And it's just a formula. And the formula is V equals I R. V is voltage. Makes sense. I is current, which makes less sense. But I is current. I used to call it intensity. All right. And then R is resistance. Now, there's a PowerPoint for this 115A, and it goes through this whole thing. And then in the PowerPoint, they show you three different versions of this equation. Okay. Which is, they show you like, well, I is V over R, which is true, but that's the same equation, right? All they did was divide both sides by R. That's the same equation. Okay. And so they show them, and I don't know, one thing you'll find, depending on if you're, what your class looks like, is your kids are going to have some level of algebra skill, but it's probably going to vary, right? There's some kids that are really going to be really comfortable with algebra, and some maybe aren't, right? And I think the reality is always that they're never as good as you expect them to be, especially not, all your kids. So I kind of take it pretty slow. I don't skip many steps, because I find that the kids that aren't as comfortable with this, it's more practice for them, and it's important. So anywho, that's my main equation. Now, some people like this thing. There's like this triangle that people do. Some people like this. And they put a V up here, and they put an I here, and they put an R over there. Sometimes people represent it as a circle. Whatever. And with this thing, what you do is you cover the quantity you want to find with your finger. So if I want to find, say, resistance, the equation is voltage over current. If I want to find current, the equation is voltage over resistance. And if I want to find voltage, the equation is current times resistance. Now, personally, Mike Crash thinks that's dumb, and this is easier for me. But over the years, I've had so many people like this that I still teach it every year, because some kid, that's the way they're going to get it. Fine. If that works for them, that works for them. I'm happy. Okay. For me, this is easier to remember, but whatever. My big complaint with this was always that you have to remember what goes where. Otherwise, this thing doesn't work, and then I had a teacher tell me, oh, yeah. The boat goes in the river. And I was like, dude, what? What? And he's like, yeah. So here's the hull of the boat. right? This little V, that's the hull of the boat, and it goes in the river. And I was like, that's dumb. And sure enough, I remember it perfectly every time. So as I always say, a mnemonic, if you remember it, it's not dumb. And I remember it. Boat goes in the river. And so now I haven't forgotten it since he said that. So boat in the river. Anyway, this is a cool, like any equation that's set up this way. There's a lot of physics equations that are set up this way, right? Like force equals mass times acceleration, and Pascal's law is set up this way, right? And so if kids like this format, they can apply it to other various physicsy equations. Anywho, that's Ohm's law. And not only is it just like a formula, I think it's a really cool look at the relationship between these three things. When we talk about building circuits, we talk about safety. I always refer back to this equation, right? I'll give a kid a colorful story. I say the voltage in your outlet in your house is 110 volts AC. That's what you're looking at. So your voltage is 110. That doesn't change, right? Your voltage is basically 110 all day, every day, regardless of what you plug into that outlet. It's 110 volts. So the only things that can change are these two things. And so I say, if you stick your fingers in the outlet, which I recommend against, you're going to get a certain amount of current through your body. It's not going to feel very good. But if you get your hands all wet when you do that, wet hands lowers your resistance. R goes down, but voltage doesn't change. So if R goes down, I has to go up. That's how math works. So this doesn't change. So R goes down, therefore I has to go up, which means if you wet your hands before you stick them in the outlet, current is going to shoot up, and current is the part of electricity that hurts. Current's the part that hurts. Current's the part that kills you. And so, I'm always like, have you ever heard like, electricity and water you don't want to mess around with? That's partly the reason, is that water lowers our resistance when it's on our skin. So it raises our current. If you plug in a billion things into an outlet, everything you plug in, you're lowering resistance, therefore you're increasing current. So it kind of describes this electrical world that we're living in, which I think is pretty cool. So when I'm trying to solve for things in a circuit, Ohm's law is my first stop. I go, do I know two of these three things? Do I know like voltage and current? Cool, I can solve for R. Do I know current and resistance? I can solve for V. If I know two of the three, I can solve for that last one, right? So that's my first step along the journey, is always to try Ohm's law. But it's not going to be enough. That's not going to be enough to solve these circuits. I'm going to add some shortcuts. Okay, we got some shortcuts. Now, a lot of people who teach this say, these are the laws. These are the series laws. And I found that when I describe them as shortcuts, I get a lot more buy-in. Kids are like, oh, shortcut, tell me more. Yeah, I like shortcuts. Okay, cool. So we got a little shortcut here. We got 3 shortcuts for series circuits, okay? So Ohm's law works for both, but these are series only. Okay, we're going to do series shortcuts first. Series shortcut number 1. Series shortcut number 1. Current is constant. I want to be really careful about this term I'm using here, though. It doesn't mean it can never change ever, ever. It means it's the same everywhere in this path. Everywhere I look, current is identical. Here, in this resistor, over here, over here, over here, wherever I look, current is the same. So if I know current in one spot, I know it everywhere. Current never changes in a series circuit. Okay, once it's sort of established. That doesn't mean like current is 7 in every circuit on the planet. No, it just means it does not change anywhere in this path. It's a great shortcut, because if I find current once, I know current everywhere. Shortcut number 2. Voltage total. So your total voltage, power supply voltage here, is the same as adding up all the individual voltage drops. So another way of saying that is like if I look at the voltage drop of this guy and this guy and this guy, it's going to add up to my total voltage. Another way of saying that is like whatever voltage you supply a circuit, it will be used up, right? If I put 1 volt into this circuit, it's going to divide proportionally between these resistors. Great. If I put 1 billion volts in this circuit, it's going to divide proportionally in these resistors. Every volt will be accounted for in this circuit. Okay. So if I add up the individual voltage drops of each resistor, it will give me the total voltage. Similarly, the total resistance, and I'm actually going to use a kind of a special order, total equivalent. The total equivalent resistance, in other words, the total resistance of this whole circuit, that's nice and easy. You just add them up. R1 plus R2 plus R3, so forth and so on. That's how you get the total resistance. So you just add up these resistors as you go. Okay. So those are our shortcuts. Now, like I said, if you look in, if you look in the official notes and everything else, you will say that this is officially called Kirchhoff's voltage law. But frankly, who cares, right? Like, it doesn't really matter that you know that Kirchhoff was the one that discovered this and whatever, right? You don't need to know that. On no test will they ever be like, describe Kirchhoff's voltage law, right? Like, no. What we need to know is that the total voltage is each of these voltages added up. That's the important part. Okay. So I'm going to do an example, but I want to pick one that's actually on your activity here. See, I have one done. Let me look and see what they have. Okay, 115. So 115, remember A, B, and C. Those are our ones that work together here. All right. So here, we're going to do this one. So we have a power supply of 9 volts. This is the one we drew in Multisim the other day. And then we have a resistor here, and a resistor here, and a resistor here. And this one is 470. This one is 1.2K. And this one is 270. One bad habit I have as a teacher is I always forget to put R1, R2, R3 on my resistors. And you wouldn't think that's a huge deal, except for then every kid in the class picks a different thing to be R1, right? Some kids think this is R1 and some kids think this is R1. Oh, it's a nightmare. So make sure you actually specify which one's which. Okay, so I like to make this little chart. Okay, I call it the scoreboard. I like to make the little scoreboard up in the corner of my whiteboard. And this is what my little scoreboard looks like. On the left side, I do voltage, current, and resistance on the left side. And on the top, I say total, R1, R2, R3, however many I need. And then I make my little chart here. Now, the first, I don't know, 3 or 4 times I do this in class, I do it by hand like this. And people say, well, couldn't you, have handouts or whatever? But, the thing is, I noticed that when I take the time to draw it, so do my students, right? If I just have it done, they're like, well, I'm not going to take the time to make a whole chart, because Crash is already writing numbers down and talking and I didn't have time. But if I sit here and I take the time to draw out this chart, the scoreboard, then the kids are likely going to do it as well. So I have my little scoreboard here. Okay. And I'll show you why I really like this. So first of all, I'm going to do my givens, right? I'm going to say, what is given? And I'm going to ask you guys this. I'm going to ask you to respond to me. What do we know already? What is given written down in the problem?
The total volts is 9 volts.
Absolutely. Nailed it,
And
Gabrielle.
3 resistors.
So total voltage. So this is my total voltage. So 9 volts goes in there. And then you said the individual resistances, right? So R1 is 470, R2 is 1.2, and R3 is 270. And so that's all my givens. Okay. Now I look at these columns and I look to see if any of these columns have 2 out of the 3 boxes filled in. Because if 2 of the 3 boxes are filled in, it's Ohm's law time. I can do Ohm's law once I have 2 of the 3 boxes in this column. Do I have 2 of the 3 boxes in any of these columns? Not yet. Only one box filled out. Only one box filled out. Only one. So I can't do Ohm's law right now. That tells me. So if I can't do Ohm's law, I jump to my shortcuts. And I say, okay, does shortcut 1 help me right now? Shortcut 1 help me with this at all?
No.
Yeah, I don't know anything about current. So shortcut 1 doesn't help me right now, right? Because if I know something, great, but I don't know anything about current right now. So shortcut 1 doesn't help me. Shortcut 2 might have helped me, but again, I don't really have enough information. I know that these 3 have to add up to that, but that's still not really enough information. So I can't really do much with that. All right. How about shortcut 3? Yeah. There, look, I know R1 and R2 and R3. So I should be able to figure out R total, the total equivalent resistance. So this is something I'm going to do in class, just like this. I'm going to say, all right, so again, I'm not going to try and do the head math on that one. I'm going to break out my calculator here, and we're going to say 470 plus 1.2 plus 270 is 741.2. And
So we have to convert.
I'll let it sit there for a second to see if somebody like Gabrielle goes, well, wait a minute, hold on. What's wrong, Gabrielle?
1.2 should be converted to 1200 because it's kilo ohms.
Oh, it's kilo ohms, 1.2 kilo ohms. And I 100% will make this mistake every time because somebody's going to make the mistake in my class. Better it happen here in front of everybody so everybody can see it. Everybody can go, oh, yeah, I did do that. I wrote 1.2. Okay. All right. So, and depending on the kids and depending on the day, sometimes I'll write everything in base units just like to further drive the point home. But I like to really point out and make that mistake. As I joke a lot with my kids, I say, 80% of the mistakes I make in class are on purpose and 20% are legitimate. All right. So instead of what I had, I have to go, and I have an erasable pen, by the way. All right. So 470 plus 1200, 1.2K plus 270. Okay. So really it's 1940. That's not proper engineering notation, but I think in the, while we're doing math with it, that's fine. I'm not presenting an answer or anything, right? I think it's fine to leave it 1940 now while we're while we're working. In fact, I prefer it because then it's less chance for kids to make a mistake as they're converting in and out of prefixes and stuff. So every time I put something in the scoreboard, I go back and go, can I do Ohm's law now? Now, can I do Ohm's law in any of these columns? Yeah, I'm seeing some nodding. Now I have 2 out of the 3, right? So here I have 2 out of the 3, which means I can do Ohm's law. So voltage total is equal to current total times resistance total. I know total voltage, that's 9 volts. I do not know current, but I do know resistance, 1940. Now watch, I'm going to say, okay, so I need to get I by itself. So I'm going to divide both sides by 1940. Those two cancel out. So I total is going to be 9 divided by 1940. Now, my math fans out there, you're like, yeah, that's basic algebra, bro. Why are you doing it like step by step by step? Because again, some kids are struggling, right? And again, more practice on that. There's nothing wrong with that, especially in a class that they're excited to be in and figure this stuff out. So 9 divided by 1940 gives me, get out of here, 0.0046339-ish. I know I've got some chemistry teachers out there probably freaking out by the significant figures situation going on here. You're going to have to keep it under control. Okay. You have to relax. Current is very small numbers. So the more you round in current, the more trouble you're going to get yourself into with precision. So especially with current, I would keep several decimals around for a while until you get till you're done. You'll notice in the slideshow too, Project Lead the Way, they're pretty good about sig figs. And so randomly you'll be like, how did this turn into 5? You know, they kind of did some sig figs and some rounding in the background and you don't see it happen. So anyway, so that's my total current. So that goes in this box right here. Now I wish I had some more room. 0.00463.9. Yikes. Now, if I was presenting this answer, I'm going to leave it base units for now, but if I was presenting it, I would move this decimal place back a 1, a 2, a 3. So that would be 4.639 times 10 to the negative 3. And that is milli. So 4.639 milliamp. Okay. Questions so far before I go any further? We're doing okay. Remember to shout out. Stop me if you need me. In the chat. Okay. All right. So same thing. I put something in the scoreboard. Check. Can I do Ohm's law? No. No spots for Ohm's law right now. So now I go to the shortcuts. Shortcut number one, help me right now. Shortcut number 1, help.
Yeah,
Michael, why does it help? Tell me what it does.
because the current's constant, so it should be the same, right?
Okay. So, and this is a great spot in your class to check for understanding / to have a little fun with your kids. Is, you know, the first one you say, okay, Michael, so tell me what is the current for R1?
It should be the same, the 0.004639.
Right. Right. I'm looking for a
And then the same
number,
for R2.
0.004639. And so then I would like either randomly or ask a kid that I wasn't totally sure if they were paying attention. I'd be like, hey, and I'm not saying Zach isn't paying attention. I'm just using him as an example. I'd be like, Zach, can you tell me what the current at R2 is?
0.004369,
And why is that, Zach?
because current is constant.
Because current is constant in a series circuit. That's right. And I'd say, Randall, do you know what the current at R3 is? I can't hear you, Randall. Randall, are you there? I can't hear you. Randall is not there. I lost Randall. Caleb, do you know what the current at R3 is
Yep, it's the same thing,
and why?
because current is constant.
Right. So what I'm doing, you hear this repetition that I'm doing, right? The more I get people to say the words that current is constant in a series circuit. Current, I might be like, Caleb, when is it? When is current's constant? Tell me it's in the series circuit, right? I say it's in a series circuit. So I get that language again and again and again. Current is constant in a series circuit. Current is constant in a series circuit. Current is constant in a series circuit, right? I'm really driving that shortcut home. Again, not that they need to memorize it, but the more comfortable they feel with it, the better. Okay. All right. Cool. Now I wrote all those in. What a wonderful shortcut. Bang, 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 bang. Filled out a bunch of boxes in one fell swoop. That was awesome. Now, can I do Ohm's law? Yeah, all over the place, right? I have 3 different spots where I can do Ohm's law here. Now, you might think then I would just kind of cruise through this, but listen to how I kind of go through this here, because I think this is pretty neat. So I'm going to do Ohm's law for R1 first. Now, I don't know voltage for R1. I don't know that, but I do know the current, which is 0.004639. And I know the resistance, which is 470. So let me just calculate that real quick. 0.004639 times 470. Okay. So I've got 2.18 volts. Now, I like to stop for a little bit of a sanity check. Those of you who have taught engineering, the math corresponds to something in real life, right? This like means something, and it's so easy to get lost in the math, right? And just do the calculations and whatever. There's a number, the calculator says 2.18, fine. But what does it mean, right? Well, it means that R1, there's 2.18 volts being dropped across R1. That's how much push or pressure to get through that resistor. Now, is it less than the total? Yeah, it is. That's a good thing, right? If you gave me a number, your calculator spat out a number, you said 21.8, I'd be like, whoa, hold on, buckaroo. It's got to be less than 9 because I know these add up to 9. Okay, cool. So now this is interesting. Look at this. R2 is a much higher resistance, 1200 as compared to 470. Much higher. But you know what's weird about that? Is the exact same amount of current got through R2 as R1. Remember, current is like if you were to count every electron cruising through there, right? So the exact same amount came through because, as you guys told me, Caleb and Zach and who else? Michael told me that the current is constant here. The exact same amount got through, even though R2 is so much harder to get through. So how did that work? How did we get the exact same amount through R2 as R1? How do we get more water through this thing?
Some more voltage or like push behind it.
Yeah, we pushed harder. Yeah, we pushed harder. This pipe was smaller. It was harder to get through here. But in order to get the exact same amount through, we had to push harder. So is this number going to be higher than that number? You betcha. Okay. Now here's an interesting thing. How much harder was it to get through R2 than R1, roughly? Estimate. 1200 to 470. Like, roughly how much harder is it?
Double.
Double?
About double.
Yeah, double. Okay, fine. Double, 3 times as much. So I bet our push is about that same. It's about double, about 3 times as much, right? So I'm going to wager that this is going to be in the 5-ish range. Let's take a look. So VR2 is 0.004639 times 1200. If I have lots of time in class, I would put that as 1.2 and make the same mistake and be like, oh, dang, 1 point. But we're in a little bit of a rush. So 0.04639 times 1200. 5.567. Something like that. So our estimation, pretty close, right? It was more than twice as hard. So we had to push more than twice as hard. Now, for the folks in your kids and people in this room that are like big math computation heads, you're like, but yeah, that's how the formula works. But you'd be surprised how many kids really like kind of light up when they're like, oh, yeah, because they can sort of visualize what these things mean, right? Like I'm pushing water through a pipe and this is a straw and this is a sewer, right? I had to push so much harder to get the same amount of water molecules through there, right? That's what we see. Now, it's estimation time again. R3 is 270. So it's actually the easiest one. This is the lowest resistance. And yet the exact same amount of current gets through. So what would you speculate? How hard do we have to push to get that current through?
Half a resistor 1.
Yeah, sure. 270 is about half 470. I know it's not exact, but about half. So I'm imagining it's about half of what we have to push R1. So it's probably in the 1-ish volts range. So I could do Ohm's law again. VR3 is 0.004639 times 270. I could do that for sure. That would give me an answer. There actually is another way I could solve this. Anybody see a shortcut that would be useful here?
Could you subtract 9? So those two values are 1 and 2 from 9.
Absolutely, because shortcut 2 says the total voltage, which is 9, has to be all these guys added up. So 9 minus this is going to give me R3. So I could do it that way too. I could Ohm's law it, or I could do this shortcut. And I'm actually going to do both just so we can see if they're the same. 0.004639 times 270 is, let's see, using Ohm's law, it's 1.2525. And subtracting 9 minus 2.18 minus 5.567. It's doing the subtraction method. It was 1.253. So why aren't those answers exactly the same? Rounding. Exactly. I rounded back here when we did our current. I rounded, I think, with one or both of these voltages. So they are the same. We just got a little creative with our rounding, which is why they're not exactly the same number. And that's okay. That's okay.
Hey, Mike, on the test, how some of the answers were like, they weren't exact, so that you pick the closest one.
Mhm.
Is that something to do with voltage and being in series, or no?
Yeah. Mm-hmm. Yep. That's right.
It is. I guess. Is that what you're saying?
Yes. Yes.
Okay, sorry.
Yeah. No, you're fine.
Michael, I always get asked by kids, like, how far to round out. Like,
Mhm.
do you set a standard at the beginning of the year or do you just kind of based on the problem, or, how do you deal with
Yeah,
it?
that's a good question. That's a good question, Gabriel. And the right answer is probably sig figs, probably significant figures, because what sig figs tell you is they tell you how precise your instrument was, right? So if a kid's like, all right, so the voltage here should be 1.254173869112, 14 or something. I'm like, dude, you have the world's most accurate multimeter. That's amazing. you had like 9 digits of precision. Oh no, I didn't. I only had 1 digit of precision. Okay, well then that's sort of a lie, right? So that's what sig figs are supposed to tell you, is how precise were your instruments in this process. So that's probably the right answer. My kids are typically juniors, and they've typically either taken or are currently in chemistry, and generally speaking, hate the concept of sig figs. And so I'm not a super big stickler on it. In the world of the electronics that we're doing in this course, these don't really matter all that much, right? If you're off by, 30 microamps, that's a pretty irrelevant difference in the scale that we're working, right? Now, if your kids go on to do like, circuit level stuff, like they're doing computer hardware engineering or whatever, then like a couple microamps is a giant deal. And then they can be more concerned about it. But at this scale, it's not really all that important. On the end of course assessment, I have noticed that kids haven't gotten things wrong because they didn't round properly, if that makes sense, right? Or they did too many digits or not enough digits. They either tells them specifically like round to 2 exact digits, or it's multiple choice, and they have never asked questions where they had 2 answers and one was the right number of digits and one wasn't, if that makes sense. So sorry, it's kind of a long-winded answer to your question, but I don't think it's that critical. Randall will probably fight me. I think Randall, you're a chemistry person, aren't
Yeah, sig figs are a battle all year long,
you? I bet.
and units.
Yeah, in units. Oof. All right. So we got to do parallel next, but I think it's going to be right about time. We're going to go right into break. So let's take a early break here. I got 55 right now. So let's come back right at the top of the hour and we'll talk about parallel. Okay. So we did series, and now we got to do parallel. Okay. So parallel, remember Ohm's law still works. Okay. So Ohm's law works whether in parallel or in series. But there are 3 parallel shortcuts. Parallel shortcuts. All right. Now, these parallel shortcuts, got to be careful because they're going to sound pretty familiar, but they're different. Okay. So for example, the very first shortcut for parallel is that voltage is constant. Voltage is constant in a parallel circuit. So anywhere you measure in a parallel circuit, you should see the same voltage. Voltage is constant in a parallel circuit. It's a neat question here you can ask your students, like, do you think your house is wired in parallel or in series, right? Like what clues do you have if your house is wired in parallel or in series, right? And the answer is that your house is wired in parallel, because regardless of where you plug something in your house, you get the same voltage out, right? That's how that works. If you plug random things in your house, it doesn't randomly change the voltage across, various things. If you plug in your TV, your toaster doesn't drop its voltage, right? Voltage is constant throughout your house. Therefore, your house is wired in parallel. Shortcut number 2. Total current is the current at R1, IR1, plus the current at R2, plus the current at R3, so forth and so on. So those first 2 shortcuts look strikingly similar to the first 2 series shortcuts, but not quite the same, right? If I look back at those, it was current is constant and voltage total is equivalent to the individual voltages added up. So shortcut 1 and 2, I have the same shortcut with current and voltage swapped. So that's what you see here in these two. And, you know, I'm very deliberate about like even the order I put them in so that like that relationship looks clearer, what changed when we went into parallel. Now, the third one is kind of weird. So the third one needs to be about resistance, R total. But parallel circuits are weird because when you add resistors in parallel, you're adding paths. You're adding more ways for electricity to get back. So every time you add a resistor, you're actually lowering the amount of resistance, which is kind of weird. Oftentimes I'll use some metaphors to try and explain this. One of my favorite ones is I'll be like, all right, so we're sitting in class and, you know, let's say that Eugene's computer just bursts into flames, just out of nowhere, just a huge fireball on Eugene's computer, right? Oh no, we're all going to get out of this room. Okay, so we're all going to leave this room. And so here's the main door of my classroom. Now, most of us are going to come running out that door. And it's a pretty big door. It's not that far away. I'd say that's our lowest resistance option. Okay, so I run out that door. Maybe they call that 100 ohms. 100 ohms of resistance to run out the main door of my classroom. Now, I happen to have a second door in my classroom that goes into another classroom. Now, maybe Tyler and Cindy decide to go out that door, but it's a couple more steps to get outside. So maybe that's 200 ohms of resistance. It's harder to get out from that door, but the most important thing to realize is overall, it actually made it easier to leave the room. There's a whole nother way to get out. So it made it easier to get out. It lowered the total resistance of this room. Okay. And then meanwhile, Laura decides she's going to like ninja flip into the ventilation system and crawl out that way, right? Way more difficult. 2,000 ohms of resistance. But even though we added a 2,000 ohm path, it still didn't make it any harder to get out of the room. It made it easier. Not much easier, I'll admit, but it made it easier to get out of the room, right? Meanwhile, Zach's over there with his pencil trying to drill a hole in the wall, and he's going to escape that way. Wildly difficult. 1,000,000 ohm resistor. And even though Zach is adding a 1,000,000 ohm resistor path, it still doesn't make it any harder to get out of the room overall. No matter what you add to this circuit, a big resistor, a small resistor, it's going to lower the total resistance. That's the way that works.
Hey, Mike, were
Yes,
you,
Greg.
were you drawing something?
I was not. I was just,
Oh, okay. Okay. I'm sorry. I didn't know because you're now. Okay. Thank you. Sorry.
I should have drawn a beautiful picture here, but I
Room. Yeah. No. Sorry.
didn't. Anywho, I've also described it or heard people describe it. Like they say you got a bucket full of water, right? And each resistor you add is like stabbing a hole in the bucket, right? And so if you add a teeny tiny pinhole or if you add a giant hole in it, regardless, you're only making it easier for water to get out of that bucket. Okay. So these long analogies are to explain, to basically apologize for this ugly equation I'm about to give you. Okay. So to get total parallel resistance, it is 1 over R1 plus 1 over R2 plus 1 over R3, R3, et cetera, et cetera. Some people prefer, there's another way to write this. It's exactly the same, mathematically speaking, but some people prefer 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3. Those are the exact same equation. Some people just prefer it in this form versus that form. It doesn't have this like nested fraction thing. Whatever. Some of my kids have like super duper fancy calculators. They can just like key this in exactly. And they're like, cool, which is fine. But that's how that works. So it's kind of obnoxious, this reciprocal equation, but that's why, right? Every time we add a resistor, it has to bring down this number, it has to bring down total resistance. So that's where this ugly equation comes in. All right. So let's practice. I'm going to pick from our activity here. I'm going to pick number 6 from our activity here. So we've got a 6-volt power supply. And we got 4 resistors going on here. There's one. This is R1, and it's 2.7K. Now, just so you know, like if I stopped right here, the total resistance of the circuit would be 2.7K because it's the only resistor, right? So by adding one, now I added R2, which is 10K ohm. Even though this is a bigger resistor, resistance had to go down. Whatever it is right now, I know it's lower than 2.7K. And I think that's a hard thing for people to understand, right? They're like, but you added 10,000 ohms. Yeah. I added a harder path, but overall, it still made it easier. I can't make it any more difficult than 2.7K. And then I add another path, R3, which is 3.3K ohms. Still making it easier. What happened to my wire there? Connect. And then R4 is 8.2K. All right. I'm going to put up my scoreboard here. And I guess I'll put it here. VIR. This time I have 4 resistors, so I'm going to need 5 columns here. Total R1, R2, R3, R4. By the way, I learned this trick about, doing this with from a college professor I had. Bob Kornowski was his name. And he would derive equations in front of us. He would never just give us an equation. He'd always derive it. I'd be like, why are you doing that? Same reason, right? Show you how to do it, that way you see it. He was one of those college professors that he like casually dropped. He's like, today we're gonna be talking about the Kornowski equation. And we're like, say what? That's your name. And he's like, yeah. We're like, so this, you invented this equation. Yeah, I mean, yeah. Okay. All right, bud. Pretty cool. Okay. So this is 115A, number 6. That's what we're working on here. 115A, number 6. Okay. We're gonna, same as always, we're gonna look at what's given. We have total voltage. So that's gonna go here. I like, it'll be like, we know voltage. I'm like, voltage of what? Total voltage. Okay, total voltage. All right, 6 volts. Okay. And we know individual resistances. Okay, so R1 is 2.7K. R2 is 10K. R3 is 3.3K. I should put the K in there. Don't be lazy. All right. And R4 is 8.2K. As always, it's not on the sheet, but as always, first step, can I do Ohm's law? No. Okay. So first step, I can't do Ohm's law. I don't have any columns with 2 out of the 3 done. No Ohm's law can happen yet. All right. So now I go to my shortcuts. Does shortcut number 1 help me right now? Yeah. Shortcut number 1 helps me a lot because voltage is constant, right? So so Tyler, you were nodding. Tyler, what's the voltage at R1?
It's all gonna be 6V
It's 6 volts. And why is that, Tyler?
because it remains constant.
What does?
Voltage,
Voltage is constant. In what kind of circuit, Tyler?
parallel.
Right. See, I'm getting to say all those words, right? Voltage is constant in a parallel circuit. Voltage is
Yep.
constant in a parallel circuit, right? And I would go around the room again, hey, Caleb, Cindy, Jordan, whatever, what's R1, R2, R3, whatever. We get this all filled out. 6 volts, 6 volts, 6 volts. Holy cow, what a wonderful shortcut. Thanks, Kirchhoff, for that one. You're the best. 6 volts all the way across because voltage is constant in a parallel circuit. Can we do Ohm's law? Now, yeah, look, Ohm's law. We can do it all over the place. Ohm's law, crazy, all over. All right, let's do one. Let's see. All right, so let's do R1 here. Okay, I'm gonna go over here with it. So voltage of R1 is current of R1 times resistance of R1. So voltage is 6 volts. Current, we don't know yet. And resistance is 2.7. Divide both sides by 2.7. Okay, there we go. 6 divided by 2.7. And in theory, that gives me 2.2-ish, repeating 2.22 amps. Does that look good? So my calculator said 2.22.
No, we had a K there.
Oh, 2.7 was K. So it's actually 2,700. Now, some of your kids probably will be like, oh, so if this 2.7 was actually times 10 to the 3, then my answer will be times 10 to the negative 3. Great. Wonderful. Thanks, those 3 kids. But most of your kids will be like, wait, what? No, I'm not okay with that. Okay. So, all right, you're right. So this answer really would be 2.22 milliamps, but let's do it the right way. 6 volts is IR1 times 2,700. Divide both sides by 2,700. And we're going to end up with, let me prove it. I don't want to, no hiding smoke and mirrors here. 6 divided by 2,700 is 0.0022 repeating, right? So 0.00222, etc. amps. If I were to move that decimal place 3 times, a 1, a 2, a 3, I would get 2.22 milliamps, which is the same as we see up here. So just kind of proving there's nothing hiding there. So I can write this in base units, 0.00222. Now, the beauty part, of course, is that its current is constant, right? So I can just come right across the line here, 0.0022, 0.0022, 0.0022, 0.0022. Oh, Tyler, what's up?
Current isn't constant in parallel circuits though, isn't it?
What? We just went over this whole thing saying current is constant. Why isn't it constant here?
Isn't it constant only in series?
It's only constant in series circuits. So here I was yelling about it, making a big deal, but it's only in series circuits. And this isn't a series circuit, is it?
No, it's
This
parallel.
is a parallel circuit. So that's a wonderful shortcut, but it only works for series circuits. Gosh, so we can't do that. It's only going to be for R1. Crash, doesn't it take longer when you do this, when you make those mistakes? Absolutely it does, but overall, it saves me a bunch of time because the kids that were going to make that mistake make it here with me and correct it right away. There's a cool book called The Talent Code by somebody. And And one of the things he found, he like looked at all the like these hotbeds of talent, right? When people got, were incredible. They looked at like Brazil and why Brazilian soccer players were like amazing. And one of the, basically the thing he found is that like practice, lots of small touches, lots of small practice with quick feedback is the fastest way to improve, right? And so that was a lot faster than me giving the assignment, Randall getting it wrong on the assignment, him giving it back to me correcting it and turning it back in, right? That's a 3-4 day process if I'm on top of my game. But right now we did it in 30 seconds, right? It's a quick turnaround. Check on that. Okay. So let's Ohm's law this next one, R2. And again, let's kind of talk about the philosophy here. So, whoops. R2 is a lot harder to get through than R1. Probably close to 3 times as, somewhere between 2 and 3 times as difficult. But we're putting the exact same amount of push on it. We're trying just as hard to get through R1 as we are R2. The exact same amount of push. Now with those series circuits, we were pushing harder or softer, but here, exact same amount of push. So what do you think is going to happen? How much current are we going to get through R2? Are we going to get as much as R1? Same amount of effort, but a more difficult journey. We're not going to get as much through, right? This is going to be lower. How much lower? Well, probably between 2 and 3 times lower. It's proportional, right? So we had, call it 2.2 milliamps. I should expect to see somewhere between 1/2 and 1/3 of that. I should see quite a bit less. So let's see, let's verify. So VR2 is IR2 times R2. So the voltage is 6 volts because voltage is constant. I'm going to solve for current. And this is 10,000. Divide both sides by 10,000. Six divided by 10,000. 0.0006. 0.0006. Which is, right, less than that. Going on to R3, again, I could probably make a pretty solid estimation. This is 0.0006, and this is 0.0022. So this is like 6, this is like 22, right? And so here, pushing same amount, easy-ish, way easier than R2, but a little bit more difficult than R1. So I'm going to expect it to be in this 22 range, but like a little bit lower, maybe 20, maybe 19. That's my rough guess. 6 volts equals current at R3 times 3,300. Divide both sides by 3,300. And by the way, in the PowerPoint, they sort of skip steps, right? They'll show this rearranged equation already and be like, IR3 is 6 divided by 3,300. And I loved it. I really like to do this intermediate step again for those kids that their algebra skills are a little weaker. And they're trying to stay with me. I think this is a good way to do it. So 6 divided by 3,300. 18. 0.00182-ish. Okay, and my last one, IR4 is times 8,200. Divide both sides by 8,200. And we see 0.00073. Still not quite as hard as R2. R2 is the toughest resistor to get through, so the least amount of current got through. 0.00073. After the first day or two of lecturing on this, I take black electrical tape and I make this grid on my whiteboard so I don't have to keep drawing it each time. It makes it easier to like erase and write these things each time, which is nice. All right, we can't rest on our laurels because we have 2 empty boxes here, but we do have a lot of options here to solve these 2 empty boxes. We can't Ohm's law, but shortcut 2 could get us there because we could add up these individual currents to find the total current. We could use shortcut 3. We could add up these individual resistors to find my total resistor. Ironically, perhaps, I don't know if irony is the right word here, but I could solve for total current and then use Ohm's law to solve for total resistance and never have to touch this yucky equation. Something to watch out for when you're teaching this is really common is people give an example where they give total voltage and all the resistances, and then you never have to do this equation. So be cautious of that as a teacher. You know, you may want to every now and again, like give current and don't give total voltage or something to change up how this problem works. So just so we can do it, let's do the total resistance equation. So our total is 1 over 2,700 plus 1 over 10,000 plus 1 over 3,300 plus 1 over 8,200 1 divided by 2,700 0.00037 plus 1 divided by 10,000 0.0001 plus 1 divided by 3,300. This is, by the way, a good time to get kids involved. Hey, you know, Caleb, can you do your calculator? Can you tell me 1 divided by 3,300? And that way, you know, kids are involved and work and they're not just watching you write numbers down. 1 divided by 8,200. 0.00012. I added all those up. I got 0.000892. Now, before I started, I said the total resistance has to be less than 2,700. And that number, admittedly, 0.000892 is less than 2,700, but that also seems like a pretty small number. That seems maybe too small for total resistance. Don't you think? That number seems kind of too small. So our sanity check is failing here. That seems like a really tiny number. What happened? Where did we make our mistake here?
We didn't divide it by 1, did we?
Correct. And that is a super common mistake for kids to make. They do this whole bottom part, the whole denominator down here, and then forget about this. It's actually 1 divided by this number. Okay. So again, I like to make that mistake and, oh, shucks, that's what it's supposed to be. 1 divided by this number. Okay, so let's do that. Let's say 1 divided by 0.000892. And that gives me 1,121 ohms. Is that less than my smallest resistor? My smallest resistor is 2,700. Yeah. So that passes the mustard there. But it's also like a reasonable number. I feel much better about that number than I do about this little one down here. So call it 1.12 K ohms. So finally, for total current, I could add up my individual currents. I could Ohm's law this. I bet, I'm not going to do them both, but I bet those two are going to be a little bit off from each other because we did a lot of rounding in these very small numbers. We did some rounding up here. So I wouldn't be surprised if these two were off a bit because of all the kind of liberal rounding we were doing in that process. But again, not a big giant deal here. Let's just do Ohm's law, just so we can get a round number. 6 divided by 1121. All right, in the neighborhood of 0.0054. Something like that. Okay. Questions about parallel or series circuit analysis?
How did you get that last current total?
Oh, I did Ohm's law. I said 6 equals, actually I didn't know, I total times 1121.
Okay.
Divide both sides by 1121. Okay. Now, this is analog electronics. And this class is called digital electronics. But without this foundation, we're going to run into trouble later in the class, right? So do kids need to be experts at doing giant series and parallel circuit analysis questions? No, not really. But let's be honest. If a kid's taking this class, they probably are looking at a career in engineering, right? And they're probably going to take physics somewhere along the way. And they're definitely going to do this in physics. And so if they haven't had it yet, this is going to help them a ton in their physics class. Or if they're going to go into any kind of electrical engineering, they're going to do this sort of circuit analysis a bunch. So, I think this is a pretty critical skill to have overall in general. Now, on your activity, they're going to ask you to do 3, 4, 5, 6, 7. Let me stop sharing here. Here we go. So they're going to ask you to do 3, 4, 5, 6, and 7. 3 we did together. So we did this one together. That was the series example we did. So there's going to be, here's number 4 is a series example to do on your own. 5 is a parallel example to do on your own. And we did 6 together. So you've got 2 of those done already. We did those together. Now 7 is what we call a series parallel or a compound circuit. Now, I will not have enough time in this cohort connection to show you how to solve that. So what I'm going to do is after this cohort connection, I'm going to stop the recording and then I'm going to start the recording again, and I'll go through how I would solve this problem. So if you have to bounce off right at the hour, that's fine. And this recording will be available to you for how to solve number 7, because that is something that you have to do for the It's Your Turn, is you have to solve number 7 here. Greg, do you have a question?
Yeah, I don't know why I struggle on your left panel on your screen finding activity 1-1, I have my, maybe I'm not even having the right page open.
Are you,
but,
yeah, does it say digital electronics up here? Or does it say something else?
Mine says digital electronics core training.
Right. So I'm in the student curriculum. So drop back to your library and go to digital electronics. That's where you're going to find it.
Oh, man. Okay. Thank you.
You're welcome. Thanks for asking.
Michael, I always struggle with problems like 7.
Mhm.
Can you just give me a hint? Because I'd like to try it by myself and I'm coming up with the wrong
Sure.
resistance, but do you pair R3 and R4 as parallel
All right.
and then combine that?
Yeah, here's my hint without getting too much into it. All the rules, all the shortcuts, everything still works, but you have to make sure you're talking about a purely parallel or a purely series portion of this circuit. And R4 and R3 are not in purely parallel because R2 is messing up the works. All right. They're not purely in parallel. If R2 wasn't here, yeah, they're purely in parallel, but it's messing things up. R1, R4, R5, like again, look like they're in series, but not because there's other branches. So the only purely something portion here is R2 to R3. This is purely series. So if I only look from this node to this node, it is a series circuit and all the series rules apply. Okay. So what I would do, and again, I'll talk more about this after the thing here, but I would take R2 and R3 and I would combine them into one resistor. I would say that the equivalent resistance between those two would be 200 plus 470, which would be 670. And then I would get rid of both of these and replace them with a single theoretical resistor that is 670 ohms, which is now in pure parallel with R4. So now your parallel rules apply and you kind of drill your way down to the power supply basically. And more, like I said, everybody, more details on that after this main session is done, because I got a bunch more things to get through here in 24 minutes. So, all right. Clear my annotations. All right. Oops. Oh, goodness. Oh, the wheels are falling off here. Okay, there we go. Whoa, clear. There we go. All right. Digital component identification. Okay. So 116, 117, and 121 we have to go through here. Okay. So 116 is another one of those discovery activities. And you've actually already done some of this in readiness training. So you may want to like peek back at your readiness training because you probably did some of these circuits already in the readiness training. If not, no big deal. You do them now. Okay. But what I actually want to focus on more here is just some like multi-sim niceties that make your life easier as you're doing 116. 116, like I said, discovery activity. So the kids, when they're doing this, they're not going to understand basically anything they're doing here. This is a lot of put it in multi-sim, see what happens and go, huh, okay, fine. Right? Because we're going to talk about it. We're going to dive in later. We're going to say, remember when that happened? They're going to say, yeah, kind of. You're like, this is why that happened. Okay. So especially towards the end of 116, I'm still sharing, right? You guys can see this. Like this stuff down here, the 555 timer and the flip flop, your kids are going to be frustrated because they're going to be like, I don't get it. And you're going to say, that's okay. It's okay. It's okay. Just observe. Just look at what happens. That's all you need to know right now. Especially this flip flop. People get all up in arms. We're going to spend like all of unit 3, like more than a quarter of this class talking about this thing right here. I promise. So don't get too worked up about not understanding this right now. We have plenty of time to talk about it. Anywho, so they're going to have you build a bunch of these circuits, and you're going to build the same thing, like a bunch. See, like that is almost the exact same thing as this. And so we are going to build some of these things. Now we need this little switch here. I'm going to build that first. And that, for those of you who don't know, is called the SPDT, single pole double throw, SPDT. Don't pick these other ones, like closed, open. Those don't simulate well. Got to pick this SPDT. Okay. Now, Multisim puts it in backwards as far as I'm concerned. I don't like the way they put it in. So I hit a little Control R for rotate. Control R rotates the thing around. If you hold it down, it spins. Whee! You show your class that, you'll burn 15 minutes. It's great. Anyway, so can rotate that around. I like it facing this way. So we've got the two lead sides on the left and the one lead side is on the right. I'm actually going to put down 2 because we're going to need 2 in a minute. So I'm going to put 2 down. The other thing that you see here that we haven't seen before is engineers being lazy, efficient. And this kind of concept here of, they call this VCC. Now, this is a shortcut saying connect this to positive power. But the more our circuits get more and more complex, there's going to be lots of things that connect to positive power, lots of things that connect to ground. And so they use these symbols to just be like, hey, these are all connecting to positive power, but we don't want a spaghetti of a billion wires all going to positive power. So this thing is called VCC. VCC. Okay. And we're going to put that down right there. Bloop. Okay. And then this one down here, this is ground, but it's digital ground. And that's DGND, digital ground, DGND. Now, if you accidentally put ground, analog ground, it actually won't matter at all. But when you build circuits, and this is sort of beyond the scope of this course, but when you build circuits that have analog parts of the circuit and digital parts of the circuit, you don't want them to have the same ground. Otherwise you get weird like voltage differential things. So that's why you see, like, we used to use that different looking ground. Now we're using digital ground. So bloop, we'll put that down there.
Hey, Mike, I'm sorry,
Yeah, Greg.
because I had a hard time getting to Multisim, and I'm writing down the components that I need.
Yeah.
but now I can't find select component because I made my screen too small.
It's under place component.
Thank you.
You're welcome. Now I got to wire this up. I'm going to take VCC. I always put it on the top leg of these switches. Because to me, if I watch my switch here, if I click it, bloop, when it's up like that, I would say like that's a 1, a high, a logic level high, a yes. That's what that means to me. When it's down like this, I would say that's like a 0 or a low. So that's how I always wire mine. In fact, I'm going to change this wire color to black because that's what they did in the activity. So I'm just kind of basically setting up a little template here to go forward. So when my little switch is down, that means I'm outputting a 0, a low, a logic 0. Remember, digital electronics is all about zeros and ones. So this is now outputting a 0. When I click it up, it's connected to 5 volts, which is what we call a digital 1, a high. Now, one question you're going to get in your class a lot, Project Lead the Way puts these little lollipops on here. They're called probes. And your kids are going to look for, and they're going to be like, I searched for X and I couldn't find it. Right. It's not called X. They just labeled it X. And I think later down here, they start labeling it. Where am I at? Yeah. They're like, they label it data in, they label it Q and tilde Q, which is Q naught. And the kids like are searching for Q or data in. They're like, I can't find it. Yeah, I know. Every single one of those is just called a probe. So when I go to place a component, I'm going to type in the word probe. Okay. So it doesn't matter which ones you use. There's just some different colors and stuff in there. The only thing I would recommend to you is not to use the probe with no color in it. I'll show you what it looks like as compared to, say, this one. Okay, so right now these probes are off. I'm at a 0, so the probes are not lighting up. They're showing me a 0. Now, when I turn them on, look what they do. So the blue one like fills in, and it's kind of obvious that it's on, whereas the other one, like you just get these little rays shooting out of it, these little lines. For me, that's a lot harder to see that this probe is on than that one. So that's why I prefer one of the colored ones, because at least like the middle fills in. That's a lot more obvious to me that it's on versus this one. But totally personal preference on that. Whatever. Okay. Let me get rid of this guy. Oops. Is your simulation running crash? Yes, it is. There we go. Okay. While these switches are here, you can, right now it says key space, which means if I hit the space bar on my keyboard, it controls that switch, which is sometimes easier than like trying to click this little bar. You guys, I'm sure will find out. You're like trying to click it, but you click this and I moved it. Oh no. Oh, right. That's an annoyance. So using the keys is nice. If you double click on your switch, you can actually choose which key controls that switch. So for example, I like to use like ASDF, like the home row, right? So like maybe that would be A, and then this one would be S. A. Now A controls my A switch, S controls my S switch, right? So that's just, again, just a nicety, just makes life a little bit easier to deal with these circuits if you want to do that. So now they want us to put in a bunch of stuff. They want us to put in this thing right here. What is this thing? Well, it's a 74LS04N. Okay, whatever that is. So I'm going to place a component and I'm going to type in 74LS04N. And it should limit me to 2 components. This one, which doesn't look anything like what they want me to put in. And this one, which does look exactly like what they want me to put in. Okay, 74LS04N. There it is. It's like triangle with a sort of circle in front of it. That's what they want me to put in. Now we're going to talk about this in just a moment, but when you try and place it, it gives you this little window. Can you guys see this little window here? Then it says new, and there's a whole bunch of letters. Your kids are going to ask you about this a lot. So what this means is in real life, when you buy an inverter from the chip store, it's going to come in a IC chip, like the ones you guys got in your supplies. And in that IC chip, there are 6 of these things, these inverters. There's 6 of them in one chip. So when you buy a chip, you don't buy 1 gate, you buy 6 of these inverters. They're all in one little package. So this question is asking me, hey, Mike, which of those 6 would you like to use right now? Now, they're all identical, so it genuinely doesn't really make a difference right now. But that's what this question is asking me. Do you want the first inverter or the second or the third or the fourth or the fifth or the sixth? Whatever. So I'm going to grab that and put it down there. It pops up immediately and goes, hey, honey, give me 1 sec. It pops up immediately and goes, hey, do you want another inverter? No, thanks. I'm good right now. That's the only one I needed. So I can hit cancel. And I'm going to add 1 more probe on the output of that. And then I'm going to ask my daughter here what she needs while you guys are wiring that. Doot. All right, I'm back. Wiring this up. We started the component. Okay. So I'm going to run my simulation. Okay. So what do I see here? Well, when I'm putting in a 0, a digital low, you see my probe is off. I get a 1 on the output. So it's going to ask you to like fill out this truth table right here. So you see, okay, so if I put a 0 in, I get a 1 out. And if I click my switch here, boop. If I put a 1 in, I get a 0 out. This is a weird spot for kids and probably you, because we just spent, however much time talking about circuits and how they work and how they're closed and everything else. And now we have this kind of weird magical device where if I put nothing into it, magically I get voltage out, which is kind of weird, but we're going to talk about that a little bit later. So that's all it's asking. Again, suppress your instinct to be like, I must understand how this works right now. We're gonna go into it, but not yet. So then for number 2 here, I got to put in a different component, 74LS08N. So I'm going to place a component, 74LS08N. Again, this symbol doesn't look like what I want. This is what I want. And when I go to place it, when you buy this thing, the 74LS08, it's called an AND gate. When you buy that from the chip store, there are 4 of them in a chip. So it's saying, hey, which one do you want? I don't care right now. I'll take A, fine. Boop. So there's A. I'm going to delete my other one. So that goes to one of the switches. And that goes to the other switch. Now I have 2 switches. So you'll see my table. Now it says, okay, X and Y, both of my switches should start at 0. Okay, so they're both low. All right, so they're both low. The output is a 0. So I'd write a 0 here in this column. And then the next combination, they say 0, 1. Okay, 0, 1. All right, the output is still 0. And then they say do 1, 0. Okay. 1, 0. The output is still low. So far 0, 0, 0. And now 1, 1. Oh, that one lit up. The output lit up. So it was 0, 0, 0. And then the last combination here gave me a 1. 0, 0, 0, 1. The light only lit up when both of the switches were on. Okay. Why? Hold your horses. We're not there yet. You're just observing. Now, just again, for make your life easier purposes, we're just going to change. Look, this next circuit is identical with a different gate. So we can check this out. We can double click on that gate and say replace. See replace right here? Replace. And they want us to replace it with a 74LS00N. The beauty part about doing replace is it keeps everything wired. Look at that. I didn't have to like delete things and rewire. Everything's already wired. So now I can just start my simulation and go, okay, 0, 0. Oh, this time it outputted a 1. And 0, 1. Oh, it's a 1. Neat. And 1, 0. It's a 1. And oh, 1, 1. It's a 0. And so you fill out your table as you go. Same thing here. Same thing here. Same thing here, etc. Okay. This flip-flop thing, again, you wire it. Big problem kids have with this, and adults and everyone, is I'm going to just zoom in. See how there's a red dot right here? That means those wires are connected. See how there's not a red dot here? That means those wires are not connected. So I'm proud of myself for remembering this because I always forget to tell people this. And then I see a bunch of circuits where this is wired together and this is wired together and this is wired together. Those wires are crossing over each other. They are not connected. This one is red dot. Those are connected. This one is, that one is, this one is. But if you don't see that red dot, those wires are crossing over each other. They're not connected. Okay.
Do they have a little icon that would do a U shape like you're going over it, or is that just not necessary?
No, you're right. They don't, Greg. They should. But Greg is right. Actually, normally in like when we're drawing these schematics, we'll draw a big loop around that wire to be like, no, these don't connect. It's a very common thing to do when you're drawing circuits. And I actually kind of wish Multisim did that, but it doesn't. Down here, 555 timer. Just my quick tips on this. You're building the exact same circuit. You're just changing the value of this capacitor down here. So I highly encourage you to copy paste this bad boy. Do the whole thing, drag a box around it, copy, paste, oops. Is your simulation running, Crash? Yeah, it is. Drag a box around it, copy, paste, but with these circuits, that way you don't have to redo it and redo it and redo it. The other thing it's going to say you should see these lights blinking at different rates. If you have like a Studley computer that can simulate really, really, really well, you might not see a big difference between these. So you might have to pick bigger changes. You got 12, 6, and 24. If you don't see a rate change, try 100 or 500 or something. That has much to do with like your computer's processing power. So you may have to change those values a little bit. Okay. All right. Last two things. 117 is about data sheets. So these things we're talking about here, these things we're putting down are called gates. And there are thousands, tens of thousands of these gates. And it is unrealistic to expect anybody to know everything about all these gates, right? And so for every gate that's ever been manufactured, they put out a data sheet. So let's talk about this one right here, 74LS00N. So if I type 74LS00N, and then I follow it with the word data sheet, I'm going to find these data sheets. And there's probably, from different manufacturers or whatever, but it doesn't matter, right? They're all the same. So if I grab this one here from alldatasheet.com, I will find a PDF of the data sheet of this chip. It shows me what the chip looks like when I buy it and what the pins represent on this chip. Here's ground, here's 5 volts, etc. It tells me all sorts of stuff I could, never possibly care about, operating temperatures, but this is really important. My truth table tells me what happens, what the gate looks like, lots and lots and lots and lots and lots of information. Most importantly, though, is this right here. Oops, this right here. Stop. This is what I care about. This is what I care about, this thing right here. Because in the It's Your Turn portion, you are going to breadboard one of these chips on your breadboard. Okay. So here's my big tip for you. The chips, let me stop my sharing. Let me turn off my oops. Oh, geez. Oh, geez. All right. The chip, look here. The chip always jumps over this alley. You don't put it over here. You don't put it over here. It's always riding this gap. The chip always goes there. Okay. There is a little half. There's no way it's going to focus. There's a little, oh yeah. There's a little half circle up at the top. and then a little circle right there, a little half circle cutout. That tells you this is the top of the chip. That tells you this is the top of the chip. And so if I go back and share now, you can see that little half circle here too. So the top left pin is pin 1, then pin 2, then pin 3, etc. Pin 7 has to be connected to ground. And pin 14 has to be connected to 5 volts. What about all this, right? So when I go to do my homework for this section, boop, bring it up. You are going to be doing one more activity that doesn't exist in the regular curriculum. So follow me here on that. I'm in the it's your turn right now. Here's the, well, here's the it's your turn. Okay. I'm in the it's your turn. 115A. We did parts of that together. Right. 116 steps 3 through 6. We were just doing that. And then here it is, here, number 7 here. Here's the thing that doesn't exist in the curriculum. Here's the only place to find it. Digital component identification. So if I click on that, they're going to ask you to breadboard these chips again. They tell you how to set up the switches, which you did yesterday. They tell you where the chip is, where the notch is, where pin 1 is. They tell you to put it over the alley. And then you're going to build this circuit right here. Okay. And again, they walk you through it pretty well, I think, piece by piece. But of course, please give me a shout if you need any help breadboarding this thing. Just to give you a little experience working with these gates. Oh, and again, number 7 and number 12 are the exact same circuit with a different chip. So just pull one chip out, put the other chip in, right? Don't build a whole nother circuit, heaven forbid. Okay. Okay. And then for your submission for 117, they're just asking for one data sheet. Just find a data sheet of any of the chips you played with in 116, the 74 LS08, the 74 LS32, the 74 LS, whatever. Pick one, Google a data sheet, show us you know how to find one on Google. That's all you have to do with that. Okay. All right. And that's plenty of reach. 121 is the last thing here. They want you to build this in Multisim. Okay. Which after you finish the other 116 and all that stuff, I feel like you should be able to build this in Multisim without too much trouble. And we're going to talk about it in our afternoon session, what this thing does. All right. Any general questions for the group before we transition to it's your turn time? Okay. I'm going to stop the recording